anyway. Now, when we're measuring flow of gases, we've got some particular problems. If we measure a litre of gas, the size of that litre is going to vary, the amount of gas is going to vary depending on the temperature. So there's a few laws involved that we need to learn about. The first law is Boyle's law. Boyle's law says that pressure and volume are related. So that if you reduce the volume, the pressure increases. Now, that's pretty obvious. Bicycle pump, when you reduce the volume, the pressure increases. That's Boyle's law. The next law is a very unfortunately named Gay-Lussac's law. He was a lovely boy. Gay-Lussac discovered that pressure and temperature are related. That when you heat something up, the pressure increases. Or when you squeeze something, the temperature increases. That's Gay-Lussac's law. If you put those laws together, we end up with a thing called the ideal gas laws. The ideal gas laws say that there's a relationship between pressure, temperature, and volume. And that relationship is a thing called the ideal gas constant. It's called the ideal gas constant because it only works for gases which are behaving the way they should. There's a lot of gases which don't behave the way they should, such as saturated steam. But that's besides the point. If we have gases behaving the way gases really should behave, they should follow the ideal gas laws. And the ideal gas laws say that mass, pressure, volume, and temperature are all related by the ideal gas constant. Here's an example of using all of those laws together. We have the inlet and outlet of a compressor. In both cases, we're talking about 1.2 kilograms of air. On the inlet side, 1.2 kilograms of air is at 20 degrees C, 1 bar, and has a density of 1.2 kilograms per cubic meter. On the outlet side, the temperature is increased because it's being compressed. The temperature is increased to 100 degrees C. The pressure has increased to 7 bar. The density has increased. It's become more compact. So it's gone from 1.2 kilograms per cubic meter to 6.5 kilograms per cubic meter. So this is the examples of the gas laws in action. Here's a comparison of different types of flow meters and their accuracies. So that's what I have for flow. One thing I do also want to tell you about is there's some specific types of liquid. And the first type of liquid I want to tell you about is semi-solids. Semi-solids are liquids that if you leave them in the cupboard for a long time, they go solid. Anybody think of a semi-solid? Cornflour. Actually, yes, cornflour is a semi-solid, and it's a very special semi-solid. Tomato sauce, paint, yes, these are all semi-solids. Now, semi-solids do special things. If you let them sit around, they go solid. If you then shake them, they go liquid. There's several semi-solids we need to worry about. Tomato sauce, sewage, and crude oil. Crude. Tomato sauce is easy enough to shake up. Sewage, if you let sewage sit around in a pipe, it goes solid. And then you're in big trouble. In fact, you're in all sorts of trouble, aren't you, really? Anyway, Crude oil, also, if crude is allowed to sit around, it will go solid. This is a big problem for the oil and gas industry. An oil pipeline generally costs tens of billions of dollars. If for any reason that pipeline stops flowing and the oil is allowed to sit in it, then you write off the pipeline. So the oil and gas industry really don't like ever stopping the flow in a pipeline. They really don't. So that's one thing to bear in mind, that you do get these semi-solids that will go solid given half a chance, and you mustn't let them. There's another whole bunch of liquids called the Newtonian liquids. Now, Newtonian liquids are basically liquids that behave themselves. They do the things that they're supposed to do. Things that liquids are supposed to do is if you shake them, they should go thinner. And if you heat them, they should go thinner. Sort of standard Newtonian liquids that do this are things like oil. If you think about your car, you start your car engine, you're supposed to start your car and then let the engine warm up. The reason you're letting it warm up is because you're letting the oil thin down so that it manages to coat all of the metalwork. So you're letting the oil thin a little bit. If you don't do this, if you jump in your car and you zoom off down the road revving it like a bugger, then you ruin your engine. So you're supposed to warm things up to make the liquid thin out a little bit. You do also have a whole bunch of non-Newtonian liquids. Now, non-Newtonian liquids are naughty liquids. They don't do what they're supposed to do. Non-Newtonian liquids, when you shake them, they go thicker. When you heat them, they go thicker. And this is where our friend corn flour comes in. Corn flour is a non-Newtonian semi-solid. It will start happily as a liquid, but you heat it up and it goes solid. The more you heat it, the thicker it becomes. Can anybody else think of anything that when you shake it, it thickens up? Paint. Yes, a thick shake. Thick shakes. You shake it and it thickens up. That's very naughty. It's behaving very non-Newtonian-y. So thick shakes, you shake them and they thicken up. Another thing, another liquid, which when you shake it or warm it thickens up, is silicon. Silicon is a very interesting liquid. It's can be quite thick, and when you shake it, it will go very thick. For that reason, silicon is used in things like bulletproof vests, because you put bags of silicon on the vest, and it moves around. It's quite flexible. It's just a bag full of liquid. But if you attack that bag full of liquid with something that's going to be hot and give it a jolly good shaking, such as a bullet, then the silicon goes solid and hopefully helps stop that bullet. At very least, it dissipates a lot of the energy. So silicon, non-Newtonian liquids used in bulletproof vests. Another place we use silicon is in what's called a fluid coupling. Has anybody heard of a fluid coupling before? Yeah, not many. Okay, what a fluid coupling looks like then, for those of you that don't know, is you've got a couple of discs, and those two discs are one's being driven from a shaft like that, and the other one, the drive is coming off. those discs have got slots in them. And they live inside a case that's completely full of silicon. So all around those discs is, all around here, all around these discs, is silicon. Now, this is used in car differentials between the back wheels, and it's also used in all-wheel drive vehicles to take the power from the rear wheels to the front wheels. And it's called it's a type of limited slip differential. Oops, let's get a better colour on it. So it's a type of limited slip differential. Because what happens is, if one side is moving quite happily, let's say for instance it's on a differential on the back wheels of a car. If one of the wheels lifts up off of the ground and just starts freewheeling round happily, then what happens is the other wheel goes stationary. That's how a normal differential would work. But with a limited slip differential, as this wheel happily freewheels round, it stirs the silicon in between. That silicon goes thicker and thicker and thicker and more solid, and as it thickens up, it produces more and more power in the second wheel until it goes completely solid and all the power is transferred across. So a limited slip differential allows you to freewheel for a little while until the silicon solidifies up, and then it locks the differential, and now you've got a locked differential and you can be pulled out of trouble. When both wheels are happily turning at the same speed, the silicon cools back down again, and now you've got a slipping differential again. So that's one use for silicon, the non-Newtonian liquid. It's used for limited slip differentials. Another use that we make for it is if you have a gauge, and that gauge is stuck on a piece of pipe, if you have any sort of pulsations going up and down on that gauge, then the poor little needle will shake itself to death. So what we do is we fill the entire gauge with silicon. If you fill the whole gauge up with silicon, so the whole thing, oops, that's not a good colour, is it? The whole of this is filled up with silicon. Now, if that gauge starts pulsing up and down, the silicon thickens up. As the silicon thickens up, it damps the pulsations. And if it pulsates a lot, the silicon goes solid and stops the pulsations altogether. So silicon-filled gauges last a lot longer than normal gauges in pulsating systems. Okay, I think I may have run out of things to tell you about. So, any questions? We've come to the tutorial part of the evening. So if anyone has any questions, I'll answer questions now.